Now, to give you an example, we've written that down. To give you an example, there could be a question on digital neural networks. The design or the application might be associated with digital neural networks, but you might come across a section worth 40% of the mark saying, compare the digital neural network with an analog neural network. So if you get full marks on that question, you need to know a good chunk of the material that is not the principal topic of the question. So it's a matter of prioritizing. Don't neglect everything other than distance classifiers or digital heads. Go through the whole syllabus, do your revision, make sure you have a broad understanding, but the focus will be on those two. And you?
Well, it will be genetic algorithm and fuzzy logic. It's personalized questions I mentioned to you already.
We've changed that, haven't we?
We haven't approved yet. At the moment we go with, but even like sort of if you practice yourself for personalized questions, so if you go for common questions, you will be able to do it because all questions will be based on calculations. Fuzzy logic, core things for calculations. Development of genetic algorithm, comparison, for example, what algorithm and when will dynamic very well behave. Analysis of dynamics of algorithm, simple. Like I'm not going to go in depth of very complex structures, but everything will cover it on the lectures, I would expect.
I mean, there's a big debate, and it's a mess again, I apologise on behalf of the university, it is a mess on this exam. There's a big debate going on as to whether exams should be face-to-face conventional, in the lecture theatre, or online. Last year they were online, and Tatiana, not everybody did this, but Tatiana and I set questions which you were doing exactly the same method, but you were using your own personal data. So you couldn't get on WhatsApp as well. Simply, a fixed data question would be add 14 plus 12. And everybody does that and has one answer. But where you're generating your own data, the question would be add your birthday day date to your birthday month date. Of course, same principle, but different data. Now this year, the university, I think, has said it's all going to be face-to-face. You've seen how many people are turning up for lectures. There should be 55 here right now. At most, we've had, what, 20 attending?
Never saw higher than 25.
And we had about 30
And we're speaking about, yeah, we're speaking about combined online and face-to-face, and I close the name to it.
And people who haven't shown up are going to be scared of a face-to-face exam. I can see enormous pressure coming from you guys, not you guys, but the student body saying, we want online exams. I suspect there are some students who haven't set foot out of Malaysia this term. And of course, another department, civil engineering, is saying they can have online exams. So you guys can take us to court, you can blow us to pieces because of the inconsistencies. So I have, under Lilla's persuasion, sat data which is fixed. So you will all be doing the same problem, assuming you'll all be face to face. And Tatiana is yet to decide.
Well, it's basically because the problem is considering your attendance and anything. We're trying to get the benefits of all cohorts. It's in our interest you pass from the first time rather than second time. Unfortunately, I don't see how it will happen this year.
We don't want.
I'm realistic. Okay. We normally had 100% pass rate, 100% attendance for whole cohort, non-stop, like for years. So for me and John, I think it's shock to see.
I'd go back 5 years and beyond that. Nobody who attended the lectures ever failed our module.
Yeah, it was always like very high grades.
Before the lockout, because things are getting difficult, you've got to earn money, and the participation in university life is getting less from the student body. 4 years ago, we were starting to get some failures, which disappointed us.
We never ever before had any retrieval for this module.
The first year of the lockdown was a complete and utter farce because everybody across the university set the standard exam paper. I think you were given 2 weeks to do it, weren't they? Mm-hmm. And you were doing the same questions. I don't have to say, I would have done the same myself. It's good engineering to fiddle the system. So we got through without too many failures in the first year of lockdown.
Guys, for revision, remember go through all my online tests. You saw, like, for example, last lecture, everyone who has done test and completed one, they were very quick to answer questions, okay? Because they already solidified the knowledge, they already have it, okay? So if you really want to make sure that you're not caught by surprise, have solidify foundational basics, so you're not getting confused.
Yeah. The second year of lockdown last year, we set exams that couldn't be copied. And the people who were engaged coped up quite easily with it. But the people who were expecting to be able to share efforts on the exam online, I mean, they were absolutely mortified. And I'll give you an example. I had a case of one guy, there was a question on analog neural networks. And he submitted, it was basically training a single node and testing it, explaining how it works. This guy submitted 37 pages of bookwork on everything he could find on analog neural networks. And I think on his diagram 5.1, there was a multi-layer network, and I just circled one node of that. From that one page, from the 37 book, this was what you were supposed to be using, this was what you were supposed to train. And how many marks can you give for copying somebody's book?
John was generous. I
gave him 1. So, the people who come in late, just to note, the main subject of the questions in my exam will be distance classifiers and digital neural networks. Now, having said that, it doesn't mean you neglect, sorry for people you've heard this, it doesn't mean to say you neglect everything in the syllabus, because the other material could come in as part of the question description. For example, if you were answering a question on digital neural networks, part of the question might say comparative behavior with analog. The focus of the design would be on the digital side.
And the questions will be very much design focused, so it means we'll be asking which design algorithm. It's not like just describe what it is, but design applying for particular problem.
Right, enough of our talking. What do you want us to talk about on material? Question 1, please. Somebody got a question?
Could you go over the phi machine, please?
The phi machine, certainly.
Do you have any questions for me so I can?
Of course I do.
Come on, guys.
Hang on, let's make a list. Before you go, Tatiana, let's make a list of all the questions.
Okay, let's go for a real quick question
Right.
here. Or if not, I can come back.
Phi machine. What other topic? Let's have a list of topics. Let's get 6 topics, and we'll prioritize them. And then whoever's got the most will stop first. Whoever's got the least. No, whoever's got the least can go first and go home. Who's got the most will stop. Next topic.
Digital neural networks.
Yeah.
You're my man, you know.
He's a smart guy. Right, 3rd topic. Come on, something for Tatiana. She's not that good a lecturer that you understand absolutely everything she said.
Maybe control uniform crossover, I guess.
Crossover.
Are you following Joe's advice? Yeah.
Next topic. Planning a party after finals. Yes, that's a good topic to discuss.
You can look a summary of this maybe.
And
Yeah. You mean about principles of building on this? Yeah. It's up on.
come on, let's complete the 6.
Hebbian learning.
Hebbian learning, yes. You said that as if you'd never heard of it before.
I did, but I just didn't take notes of it.
Last one.
the city block.
City block, this border distance classifiers. By the way, I'm not intending to turn up on the last Friday. Neither is Tatiana.
Unless it will be required.
I mean, we'll be in office if you want personal consultation, but it won't be a group meeting. So, okay, we've got 6 things. No point in taking a vote on what's the most popular. There's only 6 of you here. Fire machine, me. Digital neural networks, me. Crossover, Tatiana. Ansys, Tatiana. Heavy learning, me. 4 for me and 2 for Tatiana.
Why don't you?
You go first, and then you can go, and then
I can get my coffee out.
I'll spend the rest of the morning.
I was hoping to get coffee before, but it doesn't work. All right, guys.
I'll take you to lunch. There you are.
Ooh.
How long do you need? 20 minutes, half an hour?
20 minutes will be fast.
I'll be back at 20 to 10.
Okay, I
Enjoy.
know who wants to have a coffee now.
Yeah, I should go on for 2 hours with them, I guess.
All right, guys. Let me just have a look for ANFIS system. Remember, in ANFIS system, we have layers, and you need to remember locations of the layers and how these layers are mapped on the rules. Give me a second, I'll just run one PowerPoint slide and I'll show you something on this. And I'll show you some brief how. Oh yeah, I cannot show you slides on this again. Guys online, so you're screwing up me again, so I could show you nice. Okay, I'll be drawing. Because I was hoping to get you very quickly to ANFIS system. Okay, ANFIS system. Remember that it's very much depends on the rules you have. Okay, so ANFIS system, when we build the ANFIS system, there are several cases. First, you need to know what number of linguistic variables. I don't know, can you see it? Yeah, you can. Number of linguistic variables. Secondly, you need to know values of linguistic variables. And remember, in our case, it's input and output. And also, before we build the ANFIS system, we need to have rules. So these are 3 main elements that would help us to work on designing ANFIS system. Okay? I don't know what will be the best for you to show, but let's have a look that we have. Let's have different examples than what I was giving you in the lectures, just for you to understand how it's different. So that's how we put variation. Let's have a look that I want to design an ANFIS system. I have input X, Y, yes, and I have output Z, something like this. Okay? So let's have a look that my X will belong to linguistic variables A1, A2, and A3. So I have 3 linguistic variables. It doesn't matter what would be. It could be humidity, motor, anything else. And Y, it could be B1, B2. Okay, so now we know that we have 3 values of linguistic variable for 1, and we have 2 values of linguistic variable 2. Okay. John. So this we take into account. After we each have rules. Let's say that we have 3 rules. Rule 1, if X is A1 and Y is B1, then you, let's say our function 1, this will be like this. Rule 2, if X is A2 then F2, like this, and rule 3. If X is A3 and Y is B2, then F3. Okay, so we speak about 3 rules, slightly different than what we have agreed. Give me a second because I'm supposed to. Okay, so this is what is going on. Now we know that we have X as an input, and as input, remember our layer 1 is generation of the values, so it will be A1, A2, and A3. This will be my input for layer 1. So you see, like I open up based on one of another one, and Y, in our case, it will be B1 and B2. So our layer 1, it comes exactly the same, what I just basically line up for myself about X and Y variables. Okay. So layer 2, this is where we are implementing our rules. Okay. How many rules we have?
3.
3. If we have 3 rules, we will have 3 elements here. So this is what we are speaking about, 3 rules. First rule takes A1 and B1. Second rule takes A2. Third rule takes A2 and B2. Can you see how I'm mapping? We are literally mapping our rules on our layer 2. So this is layer 2. Layer 3, we are basically get the weighting. So layer 3 is exactly the same, and we are basically bringing inputs from each of layer 2 nodes. What I'm missing, and it's normalization. So this is where our normalized weights come in. Layer 4, where we have normalized getting in our calculation with output. And layer 5, this is when we do dephasification. So when we build down this system, what is important is to have a look on your inputs and what your outputs are. Can I just ask you, if we are speaking about 2 outputs rather than 1, how this will be modified? You'll have this one. You'll have this one. Because it will be normalized outputs coming out. But I can tell you that you will not have output 2, so you will have only output 1 output. Yeah. Number of rules, number of linguistic variables, values of linguistic variables can change.
Are we gonna need to calculate weights this year or no?
I don't remember if it's May or August. In one of exams, I was asking calculations, but I don't remember if it was May or August. I think last year was calculations of all these weights, but this year I don't remember which one I put. Cannot tell you. It could be worth to have a look. I may not ask you this year to calculate whole layers, but I may ask you to calculate, for example, first and second layer, for example.
So could you repeat what's the layer 4 for?
So this is where you get your diversification going on. Diversification. And the layer 5 is basically creates crisp output. And now if you will have a look, what is happening, you have weights like 1, for example, here. After normalization, you have normalized weight 1. After diversification, you will have normalized weight with your function 1. Yeah? And after then you are basically having a sum of weights normalized with F1. This is how it comes. Just for you to understand the calculations stream. Okay, are you happy with this? Okay, so let's have a look what you said also, crossover, yeah? Okay, I'm stuck for 10 more minutes. Is it possible that we will hold up for 10 minutes because I'm in lecture, please? Thank you very much for understanding. Sorry about this. Thank you. Bye. Okay, guys, we have 10 minutes to go. Sorry about it. All right. Crossover, uniform crossover. Remember, for the crossover, its crossover very much depends on chromosome representation. Okay. So you will need to know exactly how many numbers you have and what you have. So for example, if I have, oh, come on, what's going on? So if we are looking on case of crossover, so you need to know first what is your chromosome 1 and what is your chromosome 2. Okay, so in chromosome, like for example, let's have a look. We will have like simple 1, 2, 3, 4, 5, 6. So how many genes I have here?
6.
What is representation I'm using? It's integer representation because we have integer values, everything. Okay. So in crossover, what is important is crossover points. So if we are speaking about this, we will have one crossover point. It means that we have one point, and I can basically choose randomly. I may sometimes in the lectures, I can ask after gene, second gene. For example, in our case, it's crossover after second gene. Okay. And what we do, let me just see if I can see a different color. We get composed and new chromosomes, but containing of two different elements. So, for example, if you can see, I showed you in the blue. So we have two chromosomes. Okay. And what will be my new chromosome out of this? Can you tell me?
1, 2, 7, 8, 9, 4.
Yep. So this will be your 1-point crossover. What my second chromosome will look like?
1, 2, 7, 8, 9.
The second chromosome.
5, 6, 3, 4, 5, 6.
Yep. If I speak about 2-point chromosome crossover, what it means?
1, 2, 7, 5, 6.
So 2 points, that means I can put 1 point here, one more point here. So this will be 2 points cut. Can you see it? If it will be 2-point cut, it means I will need to add this bit after. So if we speak about 2-point cut, this is 2 point, this is 1 point. What would happen? Can someone try?
Change the middle.
So, yep,
1, 2, 7, 8, 9, 4.
yep, 9,
6,
6,
6, 5.
and chromosome 2.
5, 6, 3, 4, 5, 4.
Yeah, you got it.
What if we do 2 chromosomes in the middle, not 3? So, sorry, 2 genes in the middle, not 3.
It depends on the point. Here, for example, I put point after second and fifth. I can put this. I can put you any position of this. So it will be exactly the same principle. You need to understand principle, nothing else. It will be very much depends on these points which we are changing. And is it clear on this one? So uniform crossover. I think it's the last. Let's have a look. We have again this. Again, I have these numbers. Yeah. So I have these numbers. But what I do, instead of putting the point for break, I'm generating values between 0 and 1.
Is this random or
Randomly generated.
like our still ID?
So it's randomly, I get random generator and you generate random numbers. And so for example, let's have a look here, 0.2, 0.7, 0.9, 0.4, 0.6, 0.1. So it's randomly, you put any values between 0 and 1. I can give you and so on. Okay? And here, this is what you do. You have a border or cut, if you want. It's the value 0.5. Okay? So what you do, everything which is less than 0.5 goes in first chromosome. Everything that greater than equals 0.5 and goes in another chromosome. Yeah? So let's have a look. 1, it stays in the same. 0.7, we swap. 0.9, we swap. 0.4 stays the same. 0.6, we swap. 0.1 stays the same. So you basically swap the values only based on these random generated numbers.
Okay.
Easy?
So that random number can be our student ID.
Yeah. Simple thing.
If we still have time, maybe we can show termination criteria. If we still got time.
Termination criteria for genetic algorithm?
Yes.
What is the most popular termination criteria?
Number of generations.
Yeah. Number of generations you put straight away, so it's basically number of generations. This is the most classical case. Okay, so number of generations. This is the now. This is how you specify your termination criteria. Sometimes what is happening in our graphs, if this is our maximization problem, and this is number of generations, and this is fitness function. So instead of doing number of generations as termination criteria, what you do, you have a look with speed of convergence. So it's basically delta of number of generations, and this is delta fitness function. And you specify delta of fitness function over delta of ungeneration. So basically it's speed of convergence. And when you reach particular level of speed of convergence, you stop. Sometimes this is what is happening like termination criteria. Number of generations is the most popular. Also, nowadays, because we are getting like this algorithm starts to use in real-time systems, so instead of putting number of generations, we put time. So you put the algorithm runs, for example, I don't know, for 10 seconds, 16 seconds, or something like this. So we instead of putting number of generations, but in real times like this, it's more computationally intensive. Remember my lectures on programming. So you're looking how to implement, making sure that we use more division rather than multiplications if you want to get algorithm running faster. Yeah. So and for this, for example, considering that we have quite a bit of will be multiplications and anything, so it will be more computationally expensive to implement this termination criteria rather than this one in real-time world systems. If it's not, you could just run on this. But I'm giving you more real-world applications. Here it's foundational basics. Okay, anything else?
That's fine.
John Stoneham ran away too fast. Right. Does anyone want to have this? I'll just leave it to John to decide. I will give him the call now. Okay. I cannot because I am discharged. Okay, I'm going to go and get him. Okay.
Thank you.
You're welcome and good luck for lectures. If anyone needs help, I'll be on my.
So now I next week.
If you have questions, come to my office. If we'll have too many students have questions, you can come here on your request. I'm flexible. I am interested for you to complete, but the interest of a cohort is not on my side, I think. I'm afraid. So here it's a bit disappointing. Especially considering how many jobs are opening up in digitization, you're not getting these cool things. Okay, guys, I wish you good luck if I'll not see you. Okay, if you want to have a lecture, just send me a message and we'll do something. Okay, and I'll go and get Stoneham. Yeah.
Thank you very
Okay.
much. Thanks.
You're welcome.
In response to, oh, it's just me. I said, okay, well, there we go. Now you know it's not me. Yeah. That's the thing, like Liliana gave me the feedback like Tuesday, and I just read it. I was like, Lucas only gave me like, so he read through the entire thing, and then he said the comments. The main thing was like rewriting my abstract. So I rewrote it, made it a little bit like better, right? Because she would just dictate the feedback to me. So I thought, write it down. I would like to say, Benitez was like, I'll just send it. Yeah, still same thing. So we don't go, I'll just put comments on it. That's what it is. I'll turn on. I'm going to go and basically half of the code, 3/4 of the code will have fucking context on the middle and then today. So some steam. So lots a little bit of steam. Okay, so so we're going to yeah, do you know what it's called? Let's get conceptual. So yeah, I'm just going to be like the easiest question I could possibly. All of the people at 3 people, and it's every yeah, you know what you should do? You should go back to the maths and fucking so basically suggest you know those anti-scratch it's like people in portraits, like oh yeah, she's like that's the
Hi guys. Gosh, that was quick from Tatiana. Right. Let's try and do this in some sort of sensible order. Let's dismiss Hebbian learning first of all. It's a natural concept. It means if you have a system which depends upon variables and you are expecting a particular outcome and you are not getting that outcome, change the variables. If it makes the situation or the answer worse, go back to the original ones. If it makes the situation better, stick with the original ones. Now, lots of examples of this. If you were driving a car for the very first time and you've never experienced actually driving and moving the steering wheel. You're going down a very narrow lane. You'd start off and you'd move the steering wheel. You don't know the characteristics of the steering wheel. The car would move to the right. It's too much. You're heading for the right-hand bank. What do? You correct the steering position. So you gradually adjust. If you had a ball falling there, and it's going in a bucket there, and you have two forces on the ball there. If you wanted the ball, the direct directory to fall in the bucket would be there. If you have a force, let's call this A and B. As it falls, supposing you put a force on A, it goes to there. Maybe a force on B, and you would have a trajectory which is progressively reducing the error, and eventually the ball goes in the hole. You can use animals to demonstrate Hebbian learning. You have a series of tabs, and you have a doggy treat falling down, and they will learn to press the tabs in the right sequence to get the thing out. So that's Hebbian learning. Any questions on that? Why is it relevant to digital neural networks? Well, let's dismiss that. Let's go to the fine machine. Very briefly, the inspiration for a digital neural network, analog neural network, a McCulloch and Pitts model, was human systems. Okay. The brain, animal brain, nerves. There you have a blob which represents a nerve cell. You have inputs I, you have output, call it F. Those signals are electrical. What's going on in your brain is electrical processing. Interesting. Your thought, your vision, your whole process, the control of the body is electrical signals, which leaves loads of business opportunities, because if you interface with the nervous system, in theory, you could replicate any human activity, because human activity is measured by particular voltages. And it has lots of interesting possibilities. Some sensible ones, like controlling artificial limbs, plug into the nerves. It's hard. And if you try to do that in practice, cochlear implants is a good example. They go into the ear, they interface with the hairs that cause the transducers for sound. And a colleague of mine, Ray Glover, who used to be a lecturer here, he had a cochlear implant. First time he had the cochlear implant turned on, he was severely deaf, but he could hear and he knew what speech was. And he had to learn the patterns of that noise in his brain, changing his brain function so that becomes that sounds very strange. And the human learns. And you have to adapt. So if I take this model of the neuron, if I'm regarding it as voltages, the input F, let's call it S, that's what I'm using. S is going to be equal to I1, I2 down to IN, obviously the inputs, but they don't all count the same. They all have different influences. So we introduce a weight. So the model of this, and I'll go into 2 dimensions, is just having 2 inputs, A and B, or I1 and I2. The significance is determined by a weight, which is a number in processing. And to get the overall behavior, the simplest thing to do is to add them up with a summer and then apply a threshold. So that was the basic model of a McCulloch and Pitts neuron. Inputs, weighted, combined, and set a threshold. And the inputs are fixed. They could be measurements from the real world. If it's a face, it could be height and width of the face. Just use a very crude example. That's fixed. The only thing that would change the behavior is the weight values. And so what we are calculating in here, this point here, let's call this S. S is going to be equal to I1 times W1 plus I2 times W2. and that's just the sum of product pairs. But you guys have got a bit of mathematical knowledge. You will immediately recognize that as a mathematical operation. It is a scalar product of two vectors. I can regard I1, I2 as a point in two-dimensional space, and the vector is the distance from the origin to that pattern point. Draw it. There is a point. There's the measurement I1. There is the measurement I2. There is the pattern point, and the vector is that line. That is I. Same for the weights. They can be represented as a vector. So what this is equal to is the scalar product of the vector W with the vector I. Okay. Also, we know mathematically, two dimensions, we can see what's going on, that this also has an alternative arrangement, and that is equal to the mod of the vector W, which is the length of the vector line, times mod the input pattern cos theta. And we can draw that in two dimensions. Dimension 1, dimension 2. And if I've got my vector I there, and let's have my weight vector over here, because they can be negative. Let's have this is mod W, this is mod I, and this is cos theta. So that's what's happening in two-dimensional space. Now, if we want to classify a problem, supposing I have a problem where I have, I don't know, this is a pass exam, pass success and attendance, just to give a silly example. And supposing last year I know that the, no, that's a bad one, pass exam and nightclub hours, just a simple thing. Supposing we have from last year a set of patterns where the pass rate was very high. No, hours lecture attendance. I've got a series of patterns here, lots of attendance of lectures, very little fun afterwards. I've got another set of patterns. These are people who don't attend the lectures, and they're having a good time. And let's have a very simple model of this. The people who attend the lectures and study and don't spend all the time fun and games are going to pass. There will be exceptions, of course, life is unfair. The other group, having fun all the time, not attending lectures, fail. I can find a line which divides them. And this can be the positive class or pass, and this could be fail. Let's define that as positive and negative. That is defined by the weight vector, a single weight vector. It is at right angles to that decision surface. The surface goes through, it goes out there, and there is your W. It's not unique, there's millions of versions of them. And of course, the angle is the angle between the weight vector and the lines going to all these pattern points, which are the training vectors. So first of all, to train this system, we start off with a random weight. We know these patterns. We adjust all the patterns here so we get a positive response using Hebbian learning. Adjust all the patterns here to get a negative response, and it works on known data. That was last year's result. Now you come along this year, and let's take my friend here. He's obviously working quite hard, and he's not having much fun. He will be the vector there. I test this vector. I'll draw the vector in. I test it, I get the scalar product with the weight vector. Theta, key theta, is that there. It depends upon cos theta. Cos theta will be positive. Without drawing the system, just getting the scalar product of W with X, I will get a positive response. According to that learning system, you pass. My friend there, she's having fun all the time and not doing much work, nothing personal, but her vector is down there. So we've now got another vector there. Same W, it's fixed from training. The angle theta now is going to be greater than 90. So cos theta will be negative. The overall response will be negative. So on the negative side, sorry you failed. Go out and celebrate now and have a good time. And that's the principle. So that is a traditional analog neural network. Now this relates to digital nets because they were derived from this. This particular concept requires the patterns to be linearly separable. It will solve a problem like that, because the decision surface is there, the weight vector is out there, but it will not solve a problem like this. Because that is linearly inseparable. Can't draw a single line which will separate the red, call it A, from B. Now, of course, that's bloody obvious in 2 dimensions. You can see it. But you're not going to be using neural networks in 2-dimensional data. It is too simple. You're going to be using 10, 100, 1,000, or in the case of pictures, maybe 1,000,000 dimensions. Dimensions being the values of the features, or at high resolution, the values of the pixels. So we can't see this linear inseparability. So that's the problem with, now where was I? The limitation of an analog neural. Yes, the fix came along, 1950s, quite early on, because they built a machine which was operating not on 2 dimensions, but 16 by 24, 384 dimensions, trying to recognize characters. Princeton, 1950. Almost pre-computer age. They had to build the bloody thing with motors and variable resistors to get the weights. The system didn't work. And they had to put in a fiddle factor, which has disappeared out of the literature since then because other techniques have superseded. They put in a fiddle factor on the input. The system they might have had might have been a picture, and then the letter T. It would be extracting values, features from that. They would go into the weights, W, and they would go into the summation, and they would be out. Same sort of diagram. But what they did was realize that the system wasn't working. We need a non-linear surface, because if it was in 2 dimensions, yes, these two are separable. They don't overlap. But if I could have a surface that went like that, and like that, yes, that's positive, that's negative, it would work. Extracting single pixels means you are dealing with a linear machine, just functions of X. To get a curved surface, you've got to have the potential of functions of higher orders, functions of X squared or X cubed or quadratic or whatever. But the data was binary, black and white, noughts and ones. And then you have this horrible mathematical fact that if you have noughts and ones, and you try and apply higher order terms to noughts and ones, if X equals naught and Y equals 1, if you square them and say you want to use X squared, Y squared, naught squared would be naught, 1 squared would be 1. So you get no new information whatsoever because of the binary nature of the data. And if you had terms x, y, 0, 1, chances are most of those terms would damn well go to 0 because you've got a 0 in the multiplication. So you can't get nonlinear terms from binary. You could use different values. You could use -6 and +4. It would eliminate some of the zeros, but you would still get constant values coming from the multiplication of those two terms. So they came up with the idea in 1950 to put in a transform layer. Let's draw square boxes. And these transform layers were not taking, let's draw it again. The transform layers were not taking single points, as this was here. They are taking multiple points to try and get the higher order forms. And this would be then going into the weights. But you can't use multiplication. So they said, hey, let's use logic. Because if you use a logic function, if a is 0 and b is 1, the function is a, not a and b. But if you have a is 1 and b is 0, you get a different function, a and not b. So that will enable us to transform data using logic functions. So that was put in, they got the results at Princeton, the things sort of worked, they didn't make them a fortune, and but it did set the seed of the idea that we need this transform and higher order functions. And the early days, they were digital. So then comes along in fact, I'll leave it there. No, I'll go back to there. Where was I? We're talking about phi machines, aren't we? Yeah. Now, the phi machine is really, this was the first phi machine using logical transforms. But you can have other operations. And so the concept of the phi machine, which really was this idea of this association there, the phi machine here's my data coming in here, was a network, a transformation network, where the inputs came in and the outputs went to the net. These would be to the weights. And what goes on here is an operation which combines, let's put a few boxes in there, it will combine certain inputs to produce outputs. So there is your transformer. It's the idea of the phi machine. Now, it also has another advantage. When you're using big problems, the dimensionality kicks you. It gives you false results. Because if you have a high dimensionality problem, and you only have small numbers of examples, the system will work on a small example, but when you expand it up to a real problem, it will fail. So reducing the dimensionality of the system is a good idea. The example of that, just quickly, suppose, I think I used in the lecture, supposing I wanted to represent your gender at birth by where you're sitting. And the vectors would be the row you're sitting in and the seat number. If I were to take an example of a perfect male at birth, which is this guy here, he would be row 1, 2, 3, 4, C3, it would be 4, 3 in two-dimensional space. And if I took another example of the opposite class, in which case, wrong row, take this one here, this would be 5, 6. So those are my two training patterns. If the rest of you weren't here, we would see, bang, the decision surface gets him right, gets him right. Weight vectors going out there. If, however, I use that on a bigger data set, as you are sitting here, okay, there's my male system, okay, getting all the males right. So this is my female system, got the training pattern right, but you're wrong, you're right, you're wrong. Okay, so this will also enable us to reduce that problem, smaller dimensionality, more accurate results. And just to get to a digital neural network, which we're now at that area, it was a simple step to say the learning used to take place in the weights. Let the learning take place in this transformation layer. And that occurs in two cases, because normally the transformation is a random selection. That led to two devices in the analog system, allowing learning in this transformation system, gave us the multi-layer perceptron. Instead of having the designer randomly selecting functions here, let's have a neural network, inputs and an output to learn the transform. And that gave us the multi-layer analog net. But also the digital neural network that came about by saying we're going to set all the weights to 1. Wi equals 1 for every weight. In other words, no weights, just a connection. And then we're going to have the learning taking place in these systems. And we're going to use digital functions because we know they're good, particularly for binary data. And most data these days is binary in some form. So that gave us the concept of the digital net, which was a series of logic functions, F1, F2, and F3. It took information from an input, and clearly in the original system, the functions of a given unit in the transform layer didn't take all the inputs. It doesn't in the digital, so let's take 3 there, we take 3 there, and we take 3 there. And we build up allowable states in the logic functions, which will be the terms of the logic function. And we sum them in the normal way and set a threshold. And that will give us a network which can build up the allowable states at each sampling point. It can be used to recognize patterns. And the key thing about this is its state space behavior. The analog neural network, there's 2 classes there, is building up a decision surface which just slices through the pattern space. Everything is one class or the other. But with the digital neural network, the modeling of the state space is completely different. Take a small group of reference patterns. Supposing the patterns were, that was the one I used in the lecture, I think. And those are 3 T patterns to recognize the letter T. Can you still see it? They would be a set there, and that would be the data set, called a DT. Because the system will recognize a pattern if its allowable states in the first sampling state have occurred, and allowable states in the second state have occurred, and the third, but they don't have to occur. The same states don't have to occur in every term. You can have the first state from pattern 1 and the second state from pattern 2 in this term here. So that enables us to generalize. And that will create a generalization set. That is G, which is a set of patterns which haven't been seen, which the system recognizes. It's like training a picture of a hand. There's a training pattern there, there's a training pattern there, there's 3 of them. But having seen that, if the system only recognized those 3 patterns, it would be useless. But what we want to generalize and recognize all the ones in between. That's generalization. And if the system recognizes, so that was a training set T. If the system recognizes the data set, which is the set of all patterns which belong to that class, which you generally don't have access to, but if GT equals DT, then you've got a system that works and you earn money. Right, so what have I covered there? I think I better get on to some examples. I've really covered digital neural networks. I've covered the Phi machine. Yes, so let's have some examples. A question might ask you to compare generalization in an analog net and a digital net. That would be basically discussing those two graph behaviors. Supposing you had a problem where you are asked to recognize give us a character, B. Yes, that'll do. No, I can't do it on the resolution. Another one, please.
T.
T. Oh, I've done T. Another one.
Y.
Why? Why not? Is that a reasonable Y? Yes, that's not bad. Y, 3 by 3 low resolution. Supposing an exam question said, here is a Y. I want to use a digital neural network. I want to use 3 logic functions. I want to use RAMs to implement functions because it's trainable, variable functions. And I want to connect the system up row by row with 3 pixel samples, 3 tuple samples. Draw the diagram of the system. 20 marks for that particular question. The diagram would be the input. And let's put the pattern on there, but I won't at the moment. We're going to have 3 logic functions. The functions are connected row by row, so we take that to there, 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 and that to there, and that to there, that to there, that to there. Now F1, F2, and F3. If they are memories implementing 3-bit logic functions, how many bits, what size of memory do I want? 8 bits, spot on. Good, someone's going to pass the exam, great. So these are the 8 bits. Let's show them as 8 bits. One, 2, 3, 4, 5, 6, 7. Is it right? 1, 2, 3, 4, 5, 6, 7, 8. Yes. Going from addresses 0, 0, 0 to 1, 1, 1. Same for the others. I won't put the contents in, but initially they are set to 0. All the F's would be F equals 0. We then take the output and we sum them, and we then have a threshold to determine whether we want to accept the pattern or not. Now that would be the structure of the system. Now supposing the question went on and said, we've got to get training data. Let us train this system on that Y, but introducing on each capture of that Y, sometimes I say 11% noise. These days I usually spell it out. Noise that will change 1 pixel each time you capture the image. Now, if that image was subjected to noise and each pixel could be changed, how many training patterns do I get? 10. At least it's close. 5. Heavy learning now. 10, 5. Change it. We're heading somewhere in the middle. 7, 7, 8, 12, 9! Oh, let me draw them out for you. Noise in the first pixel. Surely I don't have to draw them all out. You got that? That is that image with one bit of noise there. Noise in the second pixel. Yes? Anybody frowning on that one? Yep. Noise on the third pixel, I'll just call them out. The third pixel with noise, top row, left, right hand side would be 1, 0, 0, 0, 1, and whatever. The fourth one in the second row, top row would be the same, middle row would be 1, 1, 0. Then the middle one disappears, and the middle row inverted. Top row the same, middle row will be 1, 0, 0, 0. Need I go on? You got the idea? Right. So, train the system on the noisy patterns. Well, the first pattern goes in there, that one goes in there. The first sample is going to be 0, 0, 1. It will set location 0, 0, 1, which will be that one. The middle sample will be 1, 0, 1, 0, which will be location 2, which is 0, 1, 2. That one will be set. Third one, the same location. And as we go through the training, the second pattern goes through. Nothing will change in functions 2 and 3 because it's the same input, but function 1 will be now 1, 1, 1, which will be location 7. That will be set. And there again is a very interesting property, because in that function, I have changed the function. The second pattern comes along, the function has got to be changed to recognize it. In terms of a logic equation, F1 on training the first pattern was going to be not A and not B and C. That term there. The second pattern comes along. This function changed, the memory has an extra bit set in. It will now respond to A and B and C. So the function now becomes not A, not B and C, or A and B and C. Simple logic. But the stunning thing about that is we haven't lost the response to the first pattern. That's why you get the clustering. Now, if you were changing weights, it's a good chance you might lose the response of the first pattern. It could become an error where it was correct. So this form of training, it is cumulative, it's defining clusters, and absolutely key important, it's a single shot training. You don't have to go back, because once a pattern is set in those functions, it never forgets the response to that function. So the third part of the question might be, determine the logical equation of the three functions, F1, F2, F3, that's a part training. Right, can we logically work it out, F1? F1, it's going to have a term when this pattern is going to be noisy, which will be not A and not B and C. 0, 0, 1, there's the noise going in there. Let's write it down there, it's going to be that. It's going to be another term when the noise is there, which will be that pattern.
You can't see the top version.
Oh, what's happening? Right. Right. This pattern, that bit of noise, that's the interval. It will be A, B, C, which is what I actually got there. The third bit of noise is going to be A, not B, not C. So do that one, which will be the term A and not B and not C. And finally, of course, the noise could be in the other lines, in which case the sample would be on the top row the same as it was to begin with. So we have the term A and not B and C. So there are 4 terms in that logic function, and that will respond to all the possible values that could occur in the top row of that character Y with noise present somewhere in the image, which changes one bit. Are you clear on that? Am I making it too simple or too hard?
But it's same for all of them, right?
It will be the same for all of them. Yes, ingenious, always look for shortcuts. Because now, no matter what the pattern is, there will be 3 patterns in the line where noise is present somewhere in that line. And there will be the 4th pattern, which is the original line, there's noise somewhere else. So F2 and F3 will have four terms. And we can make another ingenious assumption if this were an exam question, can't we? What can we say about F2 and F3? They're the same. So again, keep an eye for shortcuts. It saves time. You can slog through the first principles. An ingenious engineer will say, hey, there's a pattern there. I can go straight to that step. And tell me what you've done so I can give you extra marks for being ingenious. That's what engineers are. So that would give you the 3 equations. I won't do the rest. The principle is exactly the same. We now come to the size of the generalization set. Where are we? You lost the divider table on the other side of here. Yeah. We now come to what is the size of the generalization set there from that training set. In our case, the training set, there will be 9 crosses in the little red center. How big is the generalization set? And the question might be now the generalization for the threshold being maximum. Maximum is 3, so, and that is often referred to as AND generalization because it's the same as replacing those 2 with an AND gate. 1, 1, 1 there, the output goes to 1. If it's not 1, 1, 1, the output goes to 0. So that is called AND generalization. And generalization is G and. G and is, well, what have we got to do to get a response from F1, F2, and F3? A response of 1 from F1, F2, and F3. Well, we've got to address a 1 from the image. The image has got to address a location in this memory that is sector 1. It's also got to address from the second interval another location in the second function, which is 1. And the third one to give me 1, 1, 1, 3, threshold of 3, equivalent to AND, the output is 1, the pattern is graph. So, and also it's independent. Addressing a 1 here is completely independent of addressing a 1 here and here. So the equation from common sense for AND generalization is the product series. I equals 1. In general, the number of functions is the size of the input resolution, capital N, divided by the sample size, little n. But in this case, you can see by inspection, it is 1 to 3. 3 functions, 1, 2, 3. Doing it in the general case, 9 pixels, n equals 3, 9 over 3 is 3 functions. And the product series is a product of, I call it Ki. And Ki is number of bits set in ith function. And of course, what that is, that's a simple way of counting up the bits in the memory. But what that really is saying is the number of terms in the function. 4 bits set on training, the function had 4 bits and there are 4 terms in each of them. So if you had the Boolean equations, you would count up the number of AND terms, number of input terms. If you had the memory contents, you simply count the number of bits in each memory. And we've discovered there's going to be 4 in each. So this AND generalization is going to be Ki, it is going to be G and for I equals 1, the first function. If I've done it completely, it would be 1, 2, 3, 4. It is going to be 4. They're independent, so multiply them. The next one is 4. The next one is 4. 4 4s are 16, 64. The train net would give a maximum score of 3 out of 3 for 64 patterns trained on those 9 patterns, which is a single wire with a bit of noise. So there is the pattern. Question might go on and say, give me a pattern that gives a response 3 out of 3, passes the AND generalization, that is not one of the training patterns. Any clues?
Sorry, can you repeat that?
I want a pattern, a new pattern, which is not the Y with noise, which was used for training, so it's an independent group training, a pattern that will be recognized by that network. Well, I've got to get a 1 from the first function. I have 4 choices. Let's go for the one in the original. I want a 1 in the second pattern, but I don't want it to be the same sample as the input pattern. So a pattern in the second row, the middle row, which has 1 bit of noise, which is not in the original pattern. Let's go for and for the third one, let's go for right. Do a check. If this was input, yes, it would be outputting a 1. That's one of the set of the first interval. This pattern, 1 1 0, it is yep, one of those that is this with a bit of noise, and the bottom one is one with a bit of noise. So this pattern would have occurred in training. So we could have got that as a training pattern there. It will be recognized. That will be recognized. But combined, that pattern is not one of the noisy patterns. It's generalized. More simply, if I'm kind, I might say, what is the response of this pattern? Oh, let's take the letter T. How does a T respond to a Y detector? Positive. Give me a score out of 3. 3 out of 3? 2 out of 3? 3 out of 3. Right. Is this recognized? You can go, I haven't got the fully trained networks, but go back to the original pattern. It's got to be the top sample with 1 bit of noise. Yes, I'll get a 1 from that one. The middle row, yes, 1. The bottom row, yes, 1. It will actually recognize the T as a Y. 3 out of 3. Let's put in an L. I mean, T's and Y's, it's with 3 bits resolution. Don't hold me to perfection at this level. What about that one? What response does that give? Two out of 3. Anybody agree with that? Anybody disagree? Do you want me to go through it? I better. Right, we had top row is 1 0 0. There it is. 1 0 0. Is it an original pattern with 1 bit of noise? Yes. We will get a 1 from the top row. Middle row. 1 0 0. Started off with 0 1 0. If I put a bit of noise in there, the closest I can get to it is 1 1 0. I can't get F100. It's more than 1 bit difference from 0 to 1. Let's just check that. There is the training pattern. That can vary by 1 bit. And this is the test pattern, which is that, that, and that. No, it varies by 2 bits. That doesn't give a response. Agreed? So that gives a score of 0. And the bottom row, I think that's obvious. That doesn't give a response because it's so different. Oh, yes, it does. Yes, it does. Yes, it does. Yeah. 2 out of 3. And if you had a threshold of 3 out of 3, it would not recognize the L.
Sorry, so the functions that we did F1, F2, F3, they're required to recognize that. They just, the functions recognize
The functions are outputting a 1. What the functions are saying, that n tuple is an allowable state for a letter Y, 3-bit resolution, which might be contaminated with 1 bit of noise.
But when we do this,
When
we're
we do-
looking at the original.
When we do this, no, we put this into the functions. I've sort of gone back to the original because I haven't got the full functions out there. But what we would be putting in there would be 100, and the function was 100. It would be required to be A and not B and not C. No, 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 no. F1 would be 0.
A, not B, not C. It's the third.
Oh, yes, it's 1. Sorry, yes. 100. A and not B and not C. This is the one to go for. That's what I was meaning to do. 100. Haven't got the middle term. Let's write the middle term down. F2 and F3. F2 equals F3 equals, back to the original pattern, clean sheet of paper. There is the pattern, and we're training these middle two. Take that one. It's going to be that with 1 bit of noise. F2 equals F3 equals the original pattern where the noise is in the top row, which would be not A and B and not C. Noise on the left-hand side will be A and B and not C. Noise in the middle will be not A and not B and not C. Noise on the right-hand side will be not A and B and C. Right, so there's the 4 terms. The test pattern was L. It was the middle row, wasn't it, that was coming in, we were dealing with. The middle row would be this term here, which requires A and not B and not C. It's not a term of the function. F2 equals 0. Yes? Now that sounds a little bit long-winded. If that was the exam question, and you had the functions, and you had the block diagram with the trained memories, you haven't got to wade through these functions. All you do is for that L shape, which was the number, it was 100. For the middle row, you would go to location 1000, 1, 2, 3, 4, there's 100. You would go to that location and you would look at the contents. So you don't actually have to go through the equation. And that goes back to the general formula, why I was using the K's to get the generalization. So many papers now. Yeah, that's why I use the K's there, because I could get exactly the same result by counting the number of terms in the logic function. That's more cat-handed. Right, let's do some examples. A bit like logic in level 1. It seems impossible until you've understood that it clicks and becomes absolutely obvious. The final thing I better talk about, which I said might be a targeted topic in the exam, is distance specifiers. I think that was the last one. No, it's disappeared, never mind. Let's get those out of the distance classifier. Right, here we are getting vector representations of data. Very first distance classifier system I came across was a forensic system called FRAME, just the sort of name you need for a police system. And FRAME stood for face recognition and matching equipment. It was taking geometry of the face, height, width, distance from eye, 26 features it took out. Those were measurements, those were numbers. They became points in 26-dimensional space. Every face, every measurement, every example is slightly different. So we can't say this vector point is precisely that person. We've got to learn and generalize around it. And the strategy, they said, the obvious one, if a second vector, a second person, is very close, extremely close to another person, it's likely that they could be the same person. And these systems then were done as a preliminary search, and the candidates were passed over to a human being who would make sure that it made sense. So that was the idea. So what we're going to do in 2 dimensions, if I have pattern A there and pattern B there, and this is going to be dimension 1, let's call that A1, and this is going to be A2, B2, and B1. B1, and that's going to be dimension 2. So that's the idea. So vector, there's the vector. A equals A1, A2 as a vector. B equals B1, B2. And the distance is the key measure. If this distance D, that distance D, if that distance D is small, below a certain threshold, you are saying the smaller the distance becomes, the more similar A is to B. Now this is assuming that distance in vector space is matching perceptual similarity, not necessarily. I mean, perceptual similarity, I think I gave an example of that. If I took this as a vertical bar, and I have 2 tests, and 9 dots, if I was comparing the distance between there and the distance between those 2, perceptually, God dear, that's a bar, isn't it? A vertical bar, that's nothing, that's bugger all. But if you measure the distance, and the distance in binary will be the Hamming distance, the Hamming distance will be the difference of pixels between the 2 images, which will be the XOR of those images, all falls into place. If I've actually measured distance between, this is the known pattern, what is the distance of that from that? It's going to be 6. Yes. Different, different, same, different, different, same, different, different, same. So there will be a Hamming distance of 6. What's the Hamming distance of the bar, the perfect bar with nothing? 3. What's the closest? In terms of the distance? That's 3. That would be a bar. That one. There's a case where perceptual similarity doesn't match physical distance. But of course, what's the solution to that problem? So how can I get it to work? Image processing. And what image processing would I need? Shifting the data, run code if you like, or run code, eliminate the leading zeros, shift it so that all patterns have their black against the left hand vertical. This would shift to there, the Hamming distance between that and that then would be 0, and there would be 3, it would work. And of course, that's what humans do, because I'm looking at you, I'm getting a good picture of you. If I'm looking at him, you're very blurry. I can just about see your cap And yes. Right, so that's a little sideline. We assume that perceptual difference is the same as physical distance, and what we want to calculate is d, the distance. And if I draw this here, a right-angled triangle, the distance, let's call this distance here, it is going to be, let's call x and y. X is going to be A1 minus B1, yes. Y is going to be B2 minus A2, that distance there, and that distance there. And by simple Pythagoras, which I hope you haven't forgotten, we can work out d. And this is the Euclidean distance. In 2 dimensions, d is going to be equal to ai minus bi, a1 minus b1 squared, plus this distance, which is b2 minus a2 squared. And of course, it is the square root. So that enables you to calculate d. And of course, because the elements of the vectors are being squared, it doesn't matter which order I write them down. So for more standardized form, I can write that equal to a1 minus b1 squared plus a2 minus b2 squared. It's exactly the same because of the squaring operation and the square root. Extend it to 3 dimensions. What's the formula going to be? You could draw the geometry. It is going to be the square root of a1 minus b1 squared plus a2 minus b2 squared plus a3 minus b3 squared. By induction, you can conclude that for multi-dimensions, DE is going to be equal to the summation, we're summing them, AI minus BI, all squared, square root. Right. When we look at the use of distance, if I have a cluster there and a cluster there, supposing I can represent them with one reference pattern, it's the easiest way, but in practice you might need 10 or 100 patterns, more calculation. If I represent those clusters, they're pretty uniform by one reference pattern. If I'm using distance classification, the line of equidistance from the blue and the red X is going to be, the line joining the 2 reference patterns, the line at right angles to that is the decision surface. And that is at 90 degrees, and this point, W, is midpoint. Between A and B. So it's behaving similarly to Mercalli pits, it's creating a decision surface. Decision surface is not limited to the origin, which it is in the Mercalli pits, so it has potential. And of course, if I have 3 dimensions or 3 pattern classes, I can extend it. just score this class A. If I have a class B, it's a different colour. If I have class C down here, then you've taken 1 point for each of them. You can work out the decision surface starting in this region. A and C are dominating. The midpoint between there, the decision surface is going to come in something like that. When I get between A and B, it's going to come in something like that. And when I do these two, it comes in somewhere like that. And if you extend to the center, I think then every occasion they should meet at a point. So region, any pattern in there, class A, any pattern in there, class B, any pattern in there, class C. So that's your distance classifier. Now, in exams in the past, it can be applied to loads of applications. I think one exam paper last year, it was selecting the American election a few years back. Trump and Biden, was it? Yeah. And the story was you've got 5 parameters that you measure from the American public: education, wealth, whatever. And we've taken a set of Biden supporters, and they have a certain characteristic of that, those 5 measurements. You take Trump, and you've got another set. The idea was devise a system which will identify Trump voters, so that we can either murder them or support them, whatever. And these things have actually been used, trying to predict people's voting patterns. And never mind the application, what you have is a 5 or a 50 element vector. It was a point in pattern space, and you have for the Biden another point, and you're going to use distance to those points from you and you and you. And the closest one, you put your data in if you're an American, and you come to the Biden, vote strongly close, very similar to Biden in terms of just very close to that cluster. Then the idea is the Biden supporters will target you to get you to vote, and the Trump supporters will murder you. So it's quite useful.
Well, what's the input data? So this.
Input data, it could be wealth, you've done statistics on people, it could be wealth, it could be the car they drive, it could be surveys as well, satisfaction. Often if you take a car to a garage and you say service is satisfaction, price, whatever, and you have a range from 0 to 10. They can be converted to vectors. We can detect the people who are happy and the people who are unhappy and treat them appropriately. Shopping. You might even in exam have it doesn't really see through the application. If it says there's a vector been produced from people who do shopping and want to target them whether they're going to go on a cruise or not, forget about that. That's just the context of the distance classifier. And the development of the distance classifier, we've got 10 minutes left. If we extend the distance classifier to big data, big resolution images, like pictures, and pictures are the most common source of data around, and it's increasing. Everything is a picture now. If we increase the resolution, the dimensionality of the vector to hundreds, millions, 16 million if it's a color representation of pixels, that simple distance classification equation, where was it? That simple distance classification equation starts to take time if that's I equals 1 to d. If d is 16 million, there's a lot of computer crunching. That's just for one distance. A particular problem, you might have 10 classes, you could have 100 classes. You've got to do it 100 times more. And we're talking about clusters with only one representative pattern. What is a representative pattern? Difficult to find out. So to overcome that, you use as many patterns as you have available, which are known to you. So the number of reference patterns is not going to be 1, it could be 100 or 1,000. So we end up with a heck of a lot of number crunching to do that simple distance classifier. Solution, don't go for Euclidean distance, go for an approximate distance. And the approximate distance, I gave you two in the lectures. Can you remember what they were? City block and square. And the city block distance, dCB, equals the summation I equals 1 to D, AI minus BI, the same contents of the brackets in the Euclidean distance, but you don't square them. You simply take the mod. So you are summing the mod of the difference of corresponding elements between two vectors. And going from a multiplication, which is the squaring operation, to a mod, to get the mod of a number, think of your assembly language programming, you just drop the sign bit. Multiplication, it is a shift and add. It takes 100 times longer than just dropping a bit. The mod is a single instruction operation. So that could be 100 times faster. The square distance is it's got nothing to do with the square operation. D square is the max operator of I equals 1 to D of the mod. And that looks like a completely different way of calculating from the city block. But if you were to go and plot the contours of those three, the contours, I can draw it in 2 dimensions. I can't do it in any higher, but it will be in multi-dimensional space. If I take a pattern there, if I were to calculate the city block distance, supposing that is 0.22, I would find 0.32, I would find 0.12, I would find 0.3, yes, that's 2,2 in the middle, that's 2,2 in the middle. I would find 0.23, and I would find 0.13, equidistant from the center. If I need a fifth pattern, because that could be a circle, which would be the Euclidean distance. If I take a further pattern, let's take 2.5, 2.5. 2.5 is going to be up there, 2.5 there. I take a point there. If you've drawn it carefully, you will come to a conclusion that the contour of equidistance is not a circle. It is a line going down there. It is a line going down there. It is a line going down there. And it is a line going up there. That should be a perfect rhombus or a square on its side. And that's the contour of equidistance, which is a distortion because the true contour of equidistance, the Euclidean distance, where we want all the points at distance 1 from the center, would obviously in 2D be a circle. So the Euclidean distance, let's draw it in green, would be that perfect circle. So that is Euclidean. And this is city block. And if you were to look at the square distance, where the term square comes from, is a square contour which goes over the top. And if you draw them accurately, they all nestle. They all have the same property. At certain points, they all agree. At other points, we get considerable errors. Here we've got an error. That's the error between the city block and the Euclidean, and the city block is a smaller distance in practice. The error with the square is bigger. But then they converge, the errors disappear. So there's distortions in the error as you go in space. And that leads, if you have 2 of these sets of contours, that leads to changes in the decision surface, where if I have 2 patterns there, if I have 2 patterns there, the Euclidean decision surface, right angles, pointer in the middle, it's a straight line. That would be Euclidean, class 1, class 2. if you do the same calculation by overlapping these rhombuses or squares on the side, you will get a decision surface that looks like this. It's a dog leg. I call it a dog leg. And you can see in certain places over here, they both agree. We're on the green side of the red and the black. Over here, we're on the blue side, the red side of the two lines. But there are certain regions, the shading area, where any patterns in those regions will give a different classification depending on the metric. For Euclidean, a pattern here, it's on this side of the red surface, that would be classed with B. But if I'm using the metric that gives this decision surface, it's on the green side. Because although physically those distances look different, they are distorted because of the approximation. So you lose a bit by using approximate distance. And there is a weird situation where the city blocks, we have a class there and a class there. If they are perfectly lined up, we will have a situation where we've got let's draw a big pen to make it absolutely clear where it is. We have a situation where in the middle the decisions overlap. But when we get away from the middle, because of the precise aligning of these contours, we don't get a point intersection. We also get a line intersection. So we have a section there. Oh, bloody pens don't write. We have a line intersection there. We have a line intersection there. Taking another one out here, we have a line intersection there, a line intersection there. And the decision surface we will get comes out like this, and all this region is part of the decision surface. The dimensionality increases close to, there's the two reference patterns. Oops, sorry, 2 seconds. There's the two reference patterns. It behaves perfectly nearby. As we get further away, patterns in this region are equidistant. Now, any movement in these pattern points will cause the decision surface to flip from this dog leg, which will be the surface coming in here. We will get that dog leg like that, move that up, and we will get the dog leg like that. So the surface will flip from that to that. So if I go around the class and the invigilating doing that, that's a cue for question and answer. Work it out yourself. Do some examples. It will fall into place. And of course, the problem with that is you get false results. The distance classifier is used quite a lot. Is that class waiting to come in, was it? You coming in? Okay, guys. If you want, I'm not lecturing next week, but if you want to see me, I'll be in my office next Friday and contact me by email. And presumably you want to meet up. Do you have a week before the exams after the break? See you then, yeah? Right.
Thank you.
Cheers.
Thank you, Stonham.